Super. Welcome to our Atlas live talk this evening. So I can see that we already have a lot of people joined, and hopefully we'll get some more as they get the notification that we've just started the live. So my name is Dr. Clara Nellist. I am a particle physicist on the ATLAS experiment. This is a live talk this evening, and we're going to accept questions. You can type questions in the live chat as we go along, and we will collect them up during the talk and then ask them to our speaker at the end of the talk. So make sure any questions you have about tonight's topic, put them in the live chat. So tonight is the second talk of a series that we've been doing. So since you can't come to visit us at the ATLAS experiment, we've decided to come to you and present some of the research that we've been doing on ATLAS in these live talk sessions. So tonight's topic is linked to the spooky season. On Saturday, we have Halloween, but we also have Dark Matter Day on Saturday as well. So linked to that, we are going to have a presentation today on revealing the deep, dark secret that dominates our universe. And our speaker tonight is Dr. Christian Ohm. So let me bring up the information. So Dr. Ohm is a researcher with KTH Royal Institute of Technology in Stockholm in Sweden, which is where he is right now. And he has worked on the ATLAS experiment since 2006. His research focuses on searching for physics beyond the standard model, including scenarios that could explain what the dark matter in our universe is made of. So hopefully you're all really excited to find out more about dark matter and how we are searching for it in ATLAS. And I'm going to go ahead and hand straight over to Christian to start his talk.
All right, thanks a lot. Yeah, good evening or good morning or good afternoon to everyone listening. So yeah, thanks a lot for this fun opportunity to talk about one of my favorite mysteries in fundamental physics today, also in this fun format. So my hope is to give you out there, a sort of interested member of the general public, a taste of why the scientific community is convinced that our universe is dominated by dark matter, why that is important or interesting, and also what we're doing to try to find out what it's made of. So for the next hour, I hope that we have a chance to both talk and discuss a bit after the talk, to give you a chance to think about our place in the universe. So where everything came from, how our knowledge about the largest things we know, galaxies and clusters of galaxies, is intimately connected to how well we understand the very smallest things, the secret world of the subatomic particles. So it's also fitting to start here because this field of research is really a global effort, and the experiments rely on people from all parts of the world collaborating over long timescales to make progress. So we don't get to travel much these days, of course, but I thought we would take a virtual trip together at least. So maybe we could start by coming over to my home, which also happens to be the home of the Nobel Prize. So we zoom in on Stockholm here, and you get right to the Alba Nova University Center, where the Department of Physics is for KTH, and also Stockholm University have their physics here. So this is the campus at Alba Nova, and just around the back here is actually where I'm sitting. So this arrow right there points to the window where I'm sitting right here. Of course, now it's pitch black outside. So I'm giving this presentation from here. And the first thing I wanted to bring up is just talk a little bit about perspectives and say a quick word about scales. So we'll spend this next hour or so together. So 1 hour is 3,600 seconds. A typical work week is something like 144,000 seconds, and we can keep going. So a year is 31.5 million seconds. And if we want to talk about much longer timescales, like for example, the age of the universe, which we do want to, by the way, then this of course quickly becomes impractical. So for this reason, we'll use scientific notation. So here, 1,000 corresponds to 10 times 10 times 10, which is 10 to the third. A million is then 10 to the sixth. And for small numbers, this works the same way. And so for 1,000th, you have 10 to the minus 3. So our conventional rulers that we're all familiar with use a linear scale. And we'll use a scale, which is a logarithmic scale instead. And that means that each step along this ruler, you take a factor of 10 instead of the same distance between each tick mark on this. So with that said, let's begin our journey inwards. So what you see here is a close-up of some very blonde human hair. And at the bottom of the screen, you see one of these logarithmic scales, or one of these rulers. So here, each tick mark represents a factor of 10, and we're looking at a few millimeters here. So let's zoom in a bit. An individual hair is about 1/10 of a millimeter thick, and we're going to go pretty far in here. So we'll fast forward a bit, but the first thing you'll see here are these kinds of cells that are inside of the hairs. And then we'll see various kinds of fibers, and now we'll move a bit faster through this. And at some point here, we lose the capability of being able to see things with optical telescopes, or with optical microscopes, sorry. And what we see here is a keratin protein, and we see individual atoms here. Okay, right, so we stop at one of them, happens to be a carbon atom, really the element that is at the base of all known life. And the size of the atom is completely driven by, you see these big clouds that represent the orbitals where the electrons move around the orbit. And then we have to go very deep in to find the tiny nucleus of the atom. So this is basically 3 orders of magnitude smaller. You can see things are moving on this scale down there, and now we're down to 1 femtometer. And here you see protons and neutrons. And inside of the proton, we see 3 quarks. And protons are made of 2 up quarks and 1 down quark. And this is really as far as we get. So as far as we know, quarks are elementary, meaning they are not built up from smaller constituents. And this is the end of the line for now. Okay, so what do we know about the world of elementary particles? So over the last maybe 60 years or so, the standard model of particle physics has been established and proven to be really an incredibly successful scientific theory. So we'll start with looking at the particle content. We have organized the particles that you can see here in this little table on the right. It's almost like a periodic system where the columns represent different properties, and it's organized in a way based on properties and behaviors and roles. So we start with the matter particles, which are the fermions. So here we have 6 quarks, but in the first row here, we have the up and the down quark, and we also have the electron. And with these, you can make protons like we just saw. We can also take 2 down quarks and 1 up quark and make a neutron. And with this, together with the electrons, we can make all of the atoms and all of the elements that we know. Then in this same row at the very bottom, we have also neutrinos, and these are a bit special. So these really don't like to interact. As a measure, we get about 100 billion of those through each square centimeter of our skin that go through us completely unnoticed, and we never know. So these are very special particles. And then we have sort of 3 columns here, and they correspond to different generations, and they're exactly the same. So the up quark and the charm quark is exactly the same, and the top quark is also exactly the same, except for the mass. So when you go to the higher generations, then you go up in mass, which means that these particles can decay very quickly. Okay, so then we get to the next category of particles, which are the force particles, and these are the particles that mediate some kind of interaction between the smallest constituents that we know. So the photon, we all know quite well. It mediates the electromagnetic interaction. It's also known as the sort of light particle, but it's also the particle that makes up radio waves and X-rays and so on. The gluon holds the quarks together in the protons and the neutrons. And finally, the W and the Z bosons are responsible for the weak nuclear force, which is what makes our sun burn. So it's quite important for us also. So the last piece then is the Higgs boson, which is quite an odd one and very different from the others. But it really is of critical importance because it's responsible for giving many of the other particles their masses. So antiparticles we also have, and for almost all of these, and this sounds very exotic, but really we understand these quite well. They're just like normal particles, but they have opposite charges. So there's still a lot of, or quite some important open questions about antimatter, but we do routinely produce antimatter in our experiments, and we think we understand it quite well. Then one final thing here, we went over the different interactions and forces, and we didn't touch upon gravity. So despite being sometimes even frustratingly apparent in our everyday lives, it is incredibly weak when doing experiments between fundamental particles, and its effects are completely negligible. So as we'll see later, it is highly relevant for how our universe has evolved though. Okay, so that was the particle content. Now these pieces are connected with beautiful mathematics in what's called a quantum field theory. So this really combines two quite unintuitive theories that describe physics in sort of extreme conditions. So we have the theory of relativity, which causes strange effects at high energies, at velocities close to that of light. So time slows down and physical dimensions of objects are contracted. And we have really no experience of these conditions ourselves. So these phenomena seem very strange and foreign to us. The other quite unintuitive theory, which is combined with this theory of relativity, is quantum mechanics. And this governs the interactions on the very smallest scales, where things don't seem to be deterministic, but instead decided by chance. So you could have an electron and a positron, and they can collide, and you can create a pair of quarks, for example, and particles can be created out of nothingness. And so all of this is highly unintuitive to us. But it is an incredibly successful theory, and it really predicts and explains the decades of experimental measurements and tests. One example, we don't have to go into the detail of what it is, but it predicts the property of the electron with a precision of about 1 in 1 billion. And we can also measure this quantity with a similar precision. And as you can see, they match here, which is kind of nuts and doesn't really happen in many other fields of science. So the mathematical formulation is really beautiful and expressed in a compact way. It even fits on a t-shirt. So someone who is particularly proud of this is theoretical physicist John Ellis, who you see striking a pose here. And he takes every opportunity to remind us about this. And as it's getting now colder, or at least here in the north, it's good to know that it also fits perfectly well on a Christmas sweater. So that might be something that you could put on your list of things to purchase in the future. All right, so back to the scales that we're more familiar with. That was sort of the theory. Now let's see how we do experimental research in particle physics. So with the enormous progress made over the last, say, 100 years, we've gotten to a point where we really need large facilities that are needed for our research. So I wanted to introduce you to the laboratory that for many in our field of particle physics, including myself, has really become a second home. So we start by zooming out from Stockholm, and we get a quick view of Scandinavia and the Baltic Sea. And then we move over to Switzerland. So we go down south. And here you can see the snow-covered Alps. And we'll zoom in on the area around Geneva, which is right at the tip of the lake, the lower left here. And then on the border between Switzerland and France, we find CERN. So this shows the main site of CERN, the European Organization for Nuclear Research. And if we go across the street and dive down a little bit lower, then here we see the buildings at the ground level where the ATLAS experiment is. So you can see the mural on the wall there. And this shows what the ATLAS detector that's 100 meters below there looks like. Okay, so then what do we have there underneath? So 100 meters down, we have this really long tunnel. So it's 27 kilometers long. And in that tunnel, there are magnets and pipes that guide protons around. So it's under the border between Switzerland and France, and it's really just outside of Geneva. So we all know that nothing can travel faster than the speed of light in vacuum, but the LHC has strong electric fields that accelerate protons to really close to this magic limit. And this is to get as much energy as possible when the two beams are then brought to collide. So there are beams that go around in both directions, and then they collide at different places. So to keep the beams in orbit, very strong superconducting magnets bend the path of the particles as they travel around the ring. So in order to be superconducting, they need to be cooled down to 1.8 Kelvin. So it's very close to absolute zero. And as we'll hear also later, it's actually colder than outer space. And for this reason, some people call CERN the coolest place in the universe. So you can see that there are the four main experiments at the LHC are marked on this figure. So we have ATLAS and CMS being the largest two, and each are run by collaborations with around 5,000 members from all over the world. The two collect roughly the same amount of data from the collisions and try to use it for similar things. And you're watching the ATLAS YouTube channel right now. So of course, we'll focus on the ATLAS experiment for the rest of the talk. Okay, and here, just to give you a feeling, here's some aerial footage of the region where a sketch of the LHC is sort of superimposed, and you can also see what it looks like in the tunnel. You see it's basically 3 or 4 meters wide, and the magnets you can see there that are in an exploded view. You see the beam pipes inside of where the beams travel through. Okay, so then we get to look at the ATLAS detector. So for scale, you can see here that there are, if you look very carefully, you see tiny humans in this picture. And this is because this experiment, of course, is really huge. So here you can see that it's about 44 meters long and 25 meters in diameter, and consists of very many different kinds of detectors. So I won't go into much detail about the detectors here, but there is a really nice talk coming up as next one lined up for the YouTube channel, which is about detectors and instrumentation. And there's also a 10-minute tour of the ATLAS detector, this kind of 360 mode that's also on the ATLAS YouTube channel. So I really recommend that for knowing more about the detector. Okay, so if we then look at the collaboration that runs the experiment, so this was formed in '92 and now includes more than, or around 5,000 members, out of which about 3,000 are qualified authors and sign every paper that comes out of the experiment, from 181 institutions in 38 countries. And around 1,200 PhD students are being trained as researchers through their work on ATLAS. So many collaborators are based at their home institutes, but they go during normal circumstances, they come to CERN to help and operate the detector, do shifts in the control room, discuss and have meetings, of course, and also plan for future upgrades, etc. Okay, so what does this all look like put into motion then? So we'll have a look at here we see protons being injected in one of the earlier accelerators, smaller ones. I get into the next one, which is 630 meters in circumference. And then we enter into the SPS, which is about 7 kilometers in circumference. And then we get into the LHC, where the beams are brought up to even higher energies. And then we can see, we go inside and look in the tunnel. And here you see some graffiti of the Lagrangian from the standard model there. We cross the border between France and Switzerland. And then looking inside of the beam pipe, you see a proton here, and you see the 3 quarks inside the proton. And now this is approaching ATLAS. And there's a proton coming from the other side too. And then they collide head on right in the center and produce typically around 100 particles or so are produced in these collisions. And some of them are stopped in the earlier layers, and some of them go further out. So here you can see that there are 2 sort of larger green clusters of energy. Those are electrons, and there are 2 longer tracks that reach the outermost parts, and those are muons. So this is what it looks like when we collide particles then. So To give you a feeling for or understand a bit how we analyze the data, let's use the Higgs boson as an example. So reading this diagram from left to right, you see that on the left there, you see that there's a dashed line and an age. So this is the Higgs. And then this decays to 2 Z bosons. So it's quite rare. And then this, of course, each of these Z bosons decay to a pair of charged leptons. So it's quite rare that there are 4 charged leptons that are produced in the collisions. So when we want to try to find this type of decay, we start by selecting only those collisions. So assuming 4 leptons come from the decay of the same particle, one can actually combine the measurements of these 4 particles, take the energies and the angles, so you can calculate the corresponding mass of that particle that these would have come from. And this is what we call the invariant mass. So on the right, you see there's a histogram, and this has this mass of the 4 leptons on the x-axis. And we divide up the collisions in bins of this calculated invariant mass. And then we just count. So we enter, you can see there's 1 point there just below 100. So that's the very first event. And you can see here that there are dates up in the right corner. It says April 24, 2011. And as we start this in a little bit, then you will see that we collect more and more data, and you can see how this grows. So there are, of course, other types of collisions that look the same, though, but contain no Higgs boson. And we call those processes background processes. And we make simulations for them so that we know what to expect for the processes that don't involve the signal that we're looking for. So we start running and collecting more and more data. You can see this kind of teal filled histogram shoot up, and it matches the data quite well. So this is from the background of producing 2 Z bosons without a Higgs. And then you can see that there are some data points around 125 gigaelectron volts, which don't really look like they're described by the background simulations. And here, filling in what you expect to have for a Higgs boson that has that mass of 125 GeV, this fills in the spot perfectly. So this was one of the channels that was used for the discovery of the Higgs boson. So the Higgs boson was predicted in the 60s. The discovery was announced by Atlas and CMS on July 4th in 2012. And here you can see Fabiola Gianotti, who was the current spokesperson for the Atlas experiment during her presentation when she presented our results. So Fabiola is now the Director General for CERN, and she was recently reappointed for a second term for 2021 to 2025. So this, of course, completed the experimental verification, completed the puzzle of the standard model. So now this was the last piece to be experimentally verified to exist. And this led to the Nobel Prize for the people who predicted it back in the 60s. So of course, this is quite a long wait, and sometimes particle physics isn't for the impatient, or as Peter Higgs said it himself, I'm just very happy that it happened during my lifetime. And here you can see my favorite picture of the two during the event when they were both present in the room to hear about the discovery. Right, okay. So are we done then? This is now a very dense slide, and the point of it is to just show that across really a lot of orders of magnitude, the standard model does an incredible job, and we really can't poke a hole in it. So quantum mechanics, like we said, determines that different things can happen when we collide particles, and the different processes have different probabilities, and that's what's on this y-axis here, the different probabilities. So over, I guess it's 14 orders of magnitude here, the standard model can predict the probabilities for different processes, and then we go off and do measurements, and it matches every single time. And this is quite frustrating, of course, but it's also incredibly impressive. So the question is then, are we done? The answer is no. So there are several problems left that we don't understand in particle physics, but the one that we're talking about today is, of course, dark matter. So now we zoomed in before, now we're going to zoom out. So we start with, you see at the very top of this slide here, you see the Earth and you see the moon's orbit. And this is basically 10 to the 8 meters is the diameter of the moon's orbit. And then we have the diameter of the sun, which is 10 to the 9 meters, and 10 to the 13 is our solar system. And then we keep going out further and further. The nearest star, Proxima Centauri, is 4 light years away. That's 10 to the 16 meters. Our galaxy, the Milky Way, is 200,000 light years. And then we get to a galaxy cluster, which is something like 10 to the 23 meters. And then finally, all the way out to the observable universe, of which is thought to have a diameter of 93 billion light years. So it's now we're really going out, and this is where we have trouble to really understand things when it comes to dark matter. And this is where we see the signs of dark matter. So the first one, this is a simulation or a visualization of a galaxy and how the stars move here. And gravity gets weaker with distance. So stars orbiting the center of a galaxy are expected to have lower velocities the further away they are from the center. So you can think of the moon orbiting the Earth like we just saw. And if it moved faster, it would feel quite natural that it would sort of escape the gravitational pull and just fly out into space. And the same thing should happen with stars that are orbiting the center of a galaxy. So we expect the curve to look like the one on the left that shows the velocity on the y-axis and the distance on the x-axis, that the stars that are further out move slower. But instead, what we actually measure is something like this, that the speed seems pretty much constant. So this was this problem that there seemed to be something wrong here, it can be explained by saying that there's more mass around than the one that we can see in the form of stars and gas clouds and so on. So the first people that claimed this, maybe not necessarily exactly in the same way, but made the same claims in the 30s, was Fritz Zwicky, a Swiss astronomer. But actually a few years before him was Knut Lundmark, who was in Lund, who also said this. I think this was a few years before, so in 1930. But the main person who really convinced the scientific community with these galaxy rotation curves was Vera Rubin, who did a tremendous amount of work together with lots of collaborators, of course, in the beginning of the 70s, I would say. So this shows that there's more matter around than what we have in the shape of stars and planets and gas clouds, and this suggests that there's dark matter, and this really sort of ushered in the era of trying to understand what this is. Another piece of evidence or observation that was made is about the cosmic microwave background. So what is widely considered the first observation of very convincing evidence for the Big Bang theory was made in 1965 by accident. So radio astronomers were experimenting with the radio telescope and noticed that there was an annoying noise in their instrument. They couldn't get rid of it. And that was the same, regardless of where they pointed this antenna that you can see in the picture. So yeah, they didn't give up, and they really wanted to understand what was causing it. And it turned out that they had stumbled over a sort of unimaginable treasure for understanding the history of our universe with this cosmic microwave background. Okay, so yeah, the whole universe basically bathes in microwaves corresponding to a temperature of 2.7 Kelvin, so a little bit warmer than the magnets at CERN, that's seemingly identical in all directions. And this is really a signal from the early universe when it had cooled enough for electrons to bind nuclei to them and form neutral atoms, and then photons could travel freely. Okay. So that brings us to this picture, the evolution of the universe. And this is really one of the most beautiful pictures I know, I have to say. So it captures an incredible amount about the fundamental physics that we know, both the smallest and the largest scales, and it kind of connects everything together. It reminds us about our kind of place in the universe, but it also demonstrates how far we've come in understanding this history. But it's at the same time very humbling, because it makes it painfully clear that we have plenty left to learn. So starting from the Big Bang on the left, we can see that the different eras or different epochs of its evolution, from the inflation, when sort of everything expanded something like a factor of 10 to the 30 in 10 to the minus 30 seconds, virtually exploding our universe into existence. It was still hot and dense. And as the expansion continued, it cooled off, and this energy formed elementary particles. The quarks were bound in protons, and electrons were still flying around. So there was a hot soup of charged particles. And photons couldn't travel because they bumped into charged particles everywhere. So this effectively spread them out very evenly, and had a very sort of uniform temperature everywhere. And then suddenly, after about 380,000 years, the temperature had gone down so that the electrons were bound to the nuclei, and they formed the atoms. And the universe became transparent to electromagnetic radiation. So this perfectly sort of tempered sea of photons spread out then in all directions. They could move freely and became what we now call this cosmic microwave background. So that's what's highlighted here in red, and we'll have a closer look at that. So once this was, you can't measure this in detail on Earth because the atmosphere interferes with the signal. So you need a satellite to measure this. So there was a mission called COBE, which was conducted to measure this sort of primordial radiation in more detail. So on this map that you see here, this colorful figure, each point corresponds to a direction out in space. So regardless where we look, we saw almost the same temperature. But the small variations that are there are what you can see as the color shifts here. And they are on the order of about 10 millionths of this temperature. So about 1% of 1% of 1%. So they're tiny variations. So this was incredibly interesting to see that these variations were there, and it holds really a lot of information about how the matter in the early universe was distributed. And there were clumps in some places, and there were less matter in some other places. And so yeah, what caused this? Could something that was not interacting with light have been shaping things with its gravitational pull at this early stage of the universe? And then, of course, to see this in much more detail, another satellite was sent up with better resolution, both in the sort of spatial dimensions and also in the temperatures. So this was WMAP in 2003. And then finally, Planck released a big chunk of data in 2013, where you really have incredible spatial resolution that allows to see the size of the variations in really great detail. So we can see that there are variations both on the sort of larger scales. You see there are patches of more orange and more blue, and also on the smaller scales, these tiny dots inside of the larger patches. And here we see a way of looking at the size of the variations. So there are peaks in the size of the variation. So there's a big one around 1 degree, and there are additional bumps at smaller angular scales. So cosmologists has over the past couple of decades really become a precision discipline, and they have their own standard model, which can be used to make a fit to the data points. So the data points are the ones you see in red here. And the green line is how well this cosmological standard model fits the data. And yeah, it really shows that the best fit for this model shows that there some of the parameters in the model is the amount of dark matter in the universe. And the only way to get this to agree is that you need to have quite a lot of dark matter in the early universe, actually much more than the type of matter that we know and that we can explain by the standard model of particle physics. So, okay, that's another big important part of why we think dark matter is out there. And then gravity then keeps doing its job and slowly pulling clouds of gas molecules together, closer, packing them together, finally about 400 million years to form stars, where really the enormous gravitational pressure forces the atoms so close that they start fusing, that give rise to these natural nuclear power plants like our sun, which of course is the sort of indirect source of all the energy we use on Earth. And then 13 billion years later, we've formed galaxies, clusters of galaxies, and shaped really the large-scale structure of the universe that we live in today. And this is the next bit here. So cosmologists have their own standard model, and it can be used, like we said, it can be used to make simulations. So what you see here, you can adjust the level of atoms and the dark matter and other parameters in the early universe, and then see what kind of universe takes shape when you simulate this over billions of years. So it turns out if you don't include dark matter here, it's also very difficult to get the right distribution of the ordinary matter that we know to come into the right places. So yeah, this is just another point, another piece of evidence that points in the direction that there really must have been a lot of dark matter in the universe for most of its evolution. And you see the dark strands here in this pattern correspond to a sort of web, which is mostly made out of dark matter. And then the ordinary matter is in these bright spots where these strands intersect with each other. Okay, another fascinating effect related to gravity is the effect that it has the effect that mass has on light. So light is made of photons which have no mass, but Einstein's general relativity says that the mass curbs the space-time fabric itself, here represented by this grid. So this illustration shows how the light from a distant galaxy, which is in the back there, is bent by an in-between galaxy cluster whose mass deforms the space-time. You can see this little dip in the grid pattern there. And therefore guides the path of the light. So this is called gravitational lensing, as the gravitational pull creates a kind of lens that bends the light. So this means that an observer on Earth, down in the other corner, can see light from several directions that actually come from the same galaxy. And this means that you see rings of light. So we'll have a look at this. So in this simulation, light from galaxies in the background is distorted by the gravitational pull of an in-between galaxy with a big halo of dark matter. And then, since this is a simulation, you can just turn off the gravitational lensing, and you saw how it changed things. Okay, so with this, the last really piece of evidence that dark matter is out there is then the bullet cluster. So we say that there are two clusters colliding 4 billion light years away, but of course we're only seeing this as that signal reaches us now. So it really was colliding 4 billion years ago. And here we can see two different kinds of signal that shows where most of the ordinary mass is in pink. That's where we get X-ray signals from. And through the gravitational lensing, we can see where most of the mass is, and that's shown in blue. So it looks like the majority of the mass passed through without being stopped in this collision. And this strongly suggests that most of the mass is dark matter. So you can see the blue is kind of displaced from where all of the ordinary matter seems to have sort of got stuck, and because they interacted more and when they crossed. Okay, so there are these cosmic clues that together give a consistent, a very compelling picture that our universe is really dominated by dark matter. And in fact, looking at the matter content of the universe, the dark matter makes up about 84.5%, and the visible matter is 15.5%. So it's about 5 times more dark matter than the matter that we understand and know. So what could this be made of then? So it cannot be explained by any of the standard model particles. It's very unwilling to interact except through gravity. This we know, right? All of the evidence that we talked about so far only relies on it to interact through gravity. So it has mass, and everything we know that has mass is a particle. So it seems likely that it is a particle. But then there's really no shortage of proposals from the theory community. So it could be weakly interacting massive particles, or WIMPs as they're called. It could be axions. It could be an additional type of neutrino. It could even be some kind of smaller black holes. So primordial black holes are also allowed in some specific range of mass. So maybe it's also naive to think that it's just one particle. So we said that we only understand these 15.5% of the matter, and yet we had lots of different particles, right? So it seems likely that it could also be a more complex, rich, dark sector that has really a lot of different kinds of dark matter particles. Okay. Right, so as we mentioned before, gravity is too weak to be useful for experiments that measure interactions between individual particles. But since we know that dark matter was around in the early universe, it must have been produced through some kind of mechanism in the early stages after the Big Bang. So it seems plausible that it would interact through some other mechanism as well. And if it does that, then we can draw diagrams like this, where we have 2 standard model particles and 2 dark matter particles, and then a blob in the middle that indicates our ignorance for now. So the dark matter here is denoted as it is very often with the Greek letter chi. So we can read this diagram in different directions and get different processes between the standard model and the dark matter particles. So we start by reading it from the bottom and up, and this is where when we have what we call direct detection. So we start with 1 standard model particle and a dark matter particle, and they interact, and we end up with the standard model particle and a dark matter particle. So we think that the dark matter is spread out in this sort of halo around our galaxy, a diffuse sphere really around our galaxy. And this means that the Earth is really flying through lots of dark matter all the time, and we're facing this wind of dark matter particles. So by constructing incredibly sensitive detectors and placing them deep underground where there's very little background from radiation from space and so on, the hope is to detect little tiny recoils in the material when the dark matter particles that we fly through bump into the atoms of the detector. So one such experiment, and I should say there are many, of course, I just picked one example one, is called Xenon, or Xenon 1 ton. And they have presented very stringent limits recently on what mass and what probability it can have to interact with normal matter. So if we instead look at the diagram from right to left, like this, then we have indirect detection, where two dark matter particles interact and in fact annihilate to create two standard model particles. So for this to happen, there really needs to be a lot of dark matter around, like in the center of galaxies. So one typically looks for high energy standard model particles, maybe photons, coming from a distant source in space where we think that there's a lot of dark matter. And then we look for peaks in the energy distributions of these particles. So what's shown here, though, is an experiment that looks for charged particles primarily, called AMS, which is mounted on the International Space Station. And this measures, for example, can differentiate between electrons and positrons in space. And then, of course, the last one is collider production, which brings us back to the LHC. Okay, so we're now back at the collider, and we want to talk about how dark matter is made at a particle accelerator. So this is really the only method that depends on locally produced dark matter. So dark matter was produced in the early universe, and the LHC creates in the collisions with very high energies, recreates sort of Big Bang-like conditions, but on a very small scale. So the dark matter particles themselves don't interact, so they can't be detected in our detector. So then the question is, how can we see them? So then we use this trick that momentum is always conserved. If you think about when you go and play pool, you shoot the ball, then the amount of movement or the momentum is always conserved in those collisions. So by carefully measuring all the other particles that are produced in a collision, we can see if something escaped detection, and this gives us this missing momentum then. This is, of course, very challenging, because it means we must measure all the other particles with near perfect resolution and not miss some particles, because if we do so, that leads to fake missing momentum due to really imperfect measurements. Okay, so there have been these kinds of searches where we look for these types of events then. So here is a collision that's recorded in real data. There's a shower of hadrons that shoots up in the corner in one direction with nearly 2 tera-electron volts of momentum in the transverse plane. And then apart from this, there's not a lot of energy measured and not a lot of momentum measured. So there's a large imbalance that indicates that something escaped detection. So if you then calculate the missing momentum, there's about 2 tera-electron volts of missing momentum right opposite of the jet. So then the question is, did we discover dark matter? Of course, now we need to remember there are always backgrounds. So there are background processes that predict events like this also. For example, when you produce a Z boson together with the jet, and then the Z boson, just like it could decay to charged leptons that we saw before, it could also decay to neutrinos, which are invisible. And then it looks exactly the same like this. So they don't leave any trace in our detector. So in this case, the number of events that were seen in the data agreed perfectly with what was expected from the simulations of the background processes, which means that it doesn't look like there was any dark matter found in that particular search. So there was no trip to Stockholm awarded there. This is, of course, still very valuable, even though everyone would prefer to find new particles. Not finding them and excluding them can be very valuable for the long-term developments in trying to make progress on these questions. So when we can see that it wasn't there, then that often means that we can exclude many interesting possibilities that we would have been sensitive to, and this helps to then guide future searches. So here we can see one figure that shows this recoil that you can think of similar to the recoil between the systems here. And here you can see the stack of colored histograms represent the sum of all of the background processes that are simulated. And then the white dots represent the data. And you can see that they agree almost perfectly the whole way. So this means that instead of claiming a discovery, you would exclude parts of parameter space for these models that predict physics would look this way. So here you can see exclusion limits. This pink line shows the area which is no longer allowed, where we know we don't need to look anymore. And then we should continue looking in other places. Okay, so then what about dark matter and the Higgs? So the Higgs gives mass to the standard model particles. And the only thing really we know about dark matter is that it has mass. So the stronger coupling between the Higgs means that it has more mass. So if dark matter has mass, like we said, this is really all we actually know. It could be that the Higgs could then decay to dark matter particles and decay in an invisible way. So the LHC is the first and so far the only sort of Higgs factory where we make lots of Higgs bosons all the time, and we have an opportunity to examine them. And this provides a unique opportunity to observe evidence for these new invisible particles that could come from the decay of the Higgs bosons then that could possibly make up the dark matter. So when we're doing this, the Higgs can be produced in several different ways. And as we're looking for invisible decays of the Higgs itself, the production mechanism becomes important and can be used to select more specifically what kind of events we want. So in this one, the dark matter particles escape undetected, but the curly line that you can see that goes from left to right here, this represents the gluon, and this will give a jet of hadrons, a shower of hadrons, similar to what we saw in the previous slides with a powerful jet and then missing momentum from the escaping dark matter particles. So one can also produce a Higgs through fusion of two W bosons, and this would produce two jets from the quarks that emitted those two W bosons that then fused to form a Higgs, and they keep going in the towards the ends of the detector. And this is really a powerful handle, and you can calculate the invariant mass of these two jets, and this is a good discriminating variable for finding these kinds of events. So also this was looked for, and this is a brand new result, or quite new result, I should say. So here we see this invariant mass in a similar diagram to what we saw before, where the stacked colored histograms represent what we expect from the backgrounds, and the white dots represent what we see in the data. And as you can see, they match really well. So there's no way to claim any kind of discovery here. Okay, so then this can be converted into, and this is brand new, the new results for combining all the different searches for a Higgs that decays invisibly. And now it can be said that with 95% confidence, no more than 11% of the Higgs bosons can decay to invisible particles. It has to be a smaller fraction than that. So this is a very tight limit, and this can also be converted into a different plane where you can compare it to the other types of experiments like Xenol 1 ton you can see here, which is shown. But that's under the assumption that you look at a specific model. So the direct detection, indirect detection, and collider approaches to finding dark matter, as soon as you start comparing them, it really relies on making assumptions on what models you test. But this shows for this model that there's very nice complementarity. So the sort of turquoise line represents, the turquoise and yellow lines represent where the new limits are for the exclusions here. And what we see on the x-axis is the mass of a WIMP dark matter particle. And on the y-axis is the probability or the cross-section that these kinds of WIMPs would interact with nucleons in atomic nuclei. Right, okay. And then it's always good to think a little bit about the future and maybe if things are more complicated. So of course, there are possibilities that dark matter is produced at the LHC, but we haven't seen it yet, or we haven't looked in the right place. So there are some detector signatures that can arise if you have heavy new particles that decay to dark matter, but they actually travel a bit before they decay. And if they decay more than a few millimeters or even a few meters, then it could be that they're missed by the way that we currently analyze the data. So in fact, several theoretically appealing scenarios for dark matter include such long-lived particles to predict the amount of dark matter that we see today to be produced in the early universe. So you have a model, and then you want it to predict the amount of dark matter that we know is out there from all of these observations in space. And then to tune that, you need to tweak the parameters and introduce particles. And sometimes these particles then get a longer lifetime. So there are no heavy particles in the standard model that behave this way. And there's very little background, therefore. So it means that as we collect more and more data, these really would improve quite a lot and improve in sensitivity for these types of searches. So the little picture on the right shows a displaced vertex inside of the detector. So here's a particle that travels for a little bit and then it decays, and you can try to find it. So there are some supersymmetric theories, for example, that predict many new particles. In some scenarios, predict supersymmetric partner particles of the charged leptons of the electrons and muons and taus. So these could then decay, like you see in this diagram, to normal leptons that we can measure, and sort of a supersymmetric cousin particle that has to do with gravity, which would also be invisible then. So this decay can be suppressed since the coupling to this so-called gravitino can be very small, which means that you would have events with the two leptons that appear sort of halfway out the detector. And then you would have this missing momentum. And this could have been missed until recently. So this was targeted by an ATLAS search that specifically looked at this, but unfortunately also did not find anything, and therefore was able to exclude quite a bit of parameter space that has not been challenged for many years. Okay, so in summary, dark matter exists. It dominates our universe. There are astronomical and cosmological measurements from different parts of the history of the universe that really forms consistent and compelling evidence that there is dark matter out there. It's nothing scary. Dark matter is largely to thank that we have the opportunity to live here and experience and try to understand this only universe we know. But it is one of the biggest open questions in fundamental physics that we don't know what it's made of. There are several types of experiments that are searching for signals from dark matter. At CERN, we try to produce our own dark matter with the Large Hadron Collider. So far there's been no answers, but like we said, as soon as we don't find anything, we exclude some possibilities, and this helps to guide the future searches. And when the Higgs was found, there were actually very few places where it could still be hiding also. So of course, it has to start with looking in the wrong places, and then eventually you look in the right place. So the LHC will turn on again in 2022 and more than double the data available, and then provide 10 times more data from 2027 on after substantial upgrades. And this will be, of course, all scrutinized for dark matter. And we hope that either we at the LHC or some of these other experiments would find something. So with that, I leave you with this Halloween-themed event display of a collision in ATLAS, and look forward to your questions. Thank you.
So thank you very much, Christian, for that really interesting talk. And we've already had so many questions coming in during your presentation. So I'm going to dive right into it with the questions that we've received, both during your talk, and also we collected a few questions on Instagram just before the talk earlier today. So the first question we're going to start with is, how often are protons being collided at the LHC? Do you collide any other particles for the search for dark matter?
Right. Those are both very good questions. So about how often we collide protons. So 40 million times a second. There's 100 billion protons on one side coming in and 100 billion protons coming in from the other side. So not the sort of one-on-one proton that you saw in this simplified animation that we looked at. And then these days, roughly 35 pairs of protons collide when these bunches of protons go through each other. And that happens then 40 million times per second. So it's something like 1 billion collisions per second. And then during data taking, it's really running 24/7, or at least maybe half of the time there are collisions happening. So all of the time. About other kinds of particles, yeah, so the LHC is also used to collide heavy ions, like lead and xenon and other things. And there are some possibilities that there are certainly searches that can be done looking for particles that could make up the dark matter also in those. But I'm not an expert of those, but I know that there are ideas and plans and things being done for that, yeah.
Excellent, thank you. I've just tried to make you bigger, and I'm gonna see if that took effect. Otherwise, we might turn your slides off so that people can see you when they're answering the questions.
Do you want me to stop sharing?
Yeah, I think that would be better, and then people can see you more clearly.
Let me see if I can.
And we can play Guess the Plot in the background.
Okay, I don't see the mouse when I go to my presenter screen, and I don't dare to click anything because I might hang up.
Okay. All right, we'll
if
keep
you know
going,
the keyboard shortcut for stopping the share, then I'm happy to do that.
Okay, I think we'll go keep going as we are.
Okay.
So the next question is, where in the world are WIMPs and SUSY, and why haven't we detected them yet? Is this our failure, or does it mean that these things don't exist at all?
Yeah, so this, I think, is the beauty of doing research, that we don't know where things are hiding. We look for things that we think are well motivated, but sometimes we look in the wrong places. As far as I'm concerned, I think there's also sociological aspects of this a little bit. I think that WIMPs were really hot candidates for dark matter for such a long time, and theorists were working on this forever. And then experiments started excluding places where these WIMPs could be hiding. And then the theoretical community, of course, want to look at other things and other scenarios too. But it's not like the whole WIMP parameter space is excluded. And if we stopped looking for the Higgs when it could only be in a few places, then that would have been a bit weird, I think. So I think as experimentalists, we should really try to cover all unexcluded, well-motivated space for different models. And not just follow sort of what seems to be a hot topic for the year or for the month. But there are certainly many fun things to look for. So I'm not saying we should only look for WIMPs.
Great, thank you. And I think Sasha's just managed to remove your slides. So
perfect.
We'll see the effect of that in a moment. So yeah, great, thank you. Yeah, I think it's really important to emphasize that we have to look everywhere, and we never know what we're going to find, especially now that we don't have the roadmap of the Higgs. So looking in many different places is very important. So the next question we have is, how do you think its discovery, dark matter, will affect science if we find out what it's made of?
Yeah, first of all, I really do think that we'll need several types of experiments seeing something. So if we were to see an excess of events that look like they could come from, could be events where dark matter particles are produced, that's not enough to convince everyone that that's the explanation for dark matter. It could be any kind of particle, and it doesn't have to play that role, that critical role in the history of the universe. And we can, of course, if we could see signals that match from two different types of experiments, so say that indirect detection and collider, or direct detection and indirect detection, would see something that matches, and where there's a theory that can describe both of those measurements, I think that would be huge, and that would really steer the whole experimental program for probably for decades, to try to really do more precise measurements of whatever signal is observed.
So this then leads perfectly into our next question, which is, what if dark matter doesn't exist? What if we were wrong?
Yeah, it could happen. At this point, it seems really like the scientific community is, I would say, basically 100% convinced that dark matter must be there. Then, of course, many things, it might not be as simple as we said. one of the things I mentioned in the talk is that this whole dark sector could be much more complex than just having one particle. And that I think is important to keep in mind. I don't know if there could also be that you had one kind of dark matter during some part of the evolution of the universe, and then this decayed or transformed into another type, which would mean that we have to really think about what we're trying to find now, and it doesn't have to necessarily have the same properties as what was around in the early universe. Yeah, I don't know if that answered the question.
Yeah, I think it does. We'll also find out in the chat if people have any follow-up questions. I should also mention, by the way, there were lots of thank yous in the chat after the end of your talk, so it was appreciated.
Thanks for listening. Yeah.
Okay, so the next question we have is, should we modify the standard model if we find dark matter?
Well, so I think the standard model is really fantastic as it is. And we talked about that a little bit. It's really incredible the predictive power it has, and it's withstood experimental tests for decades. But what we're talking about, I wouldn't see it as we have to change the standard model. That part of the theory seems really great, but we need to extend it to include also whatever more physics is needed to explain the dark matter. So that's, I think, how I would see it.
Okay, great. And now, so we hear a lot about machine learning and artificial intelligence in research and in other areas of life. So does machine learning help in dark matter research, and how?
I think it does. Yeah, I think so. For a very long time, research in experimental particle physics really produced tons of data, and therefore also had to develop methods for statistical analysis and really drive the development of such methods. But of course, with society being completely digital these days, then there's data about everything, then there's a lot of money to make, and therefore there are these other actors in the world that really push these and push them hard, these new methods. And of course, we have lots to learn there on all kinds of levels. It could improve our simulations, help them run faster on our computers and save resources that way. It could help to reconstruct low-level detector data to more precisely say, okay, a particle went through here, these are the hits that we see in the detector. And then those types of algorithms or those types of methods can then help us to do better measurements with the detectors that we already have. And then also to separate signals from backgrounds. This is also typical tasks. I think that's also I mean, it has been used for a long time and is being used. So definitely there's a strong connection there.
Great. So the next question goes on to what do you think about anomaly claims? So a few years ago, there were potential hints of something that then eventually went away. And so how do they affect the scientific community when these come out?
Yeah, I think it's a good question. I think it affects us as experimentalists maybe a little bit less than other parts of our community. We have our huge projects that run for very long timelines with very clear goals for, and we're quite busy. So of course we're excited if there are hints of new signals showing up, but the timeline for our projects are so long that we can't just really change too much anyway. It's easier if you're working on developing theories, for example, and then there's some interesting observation. Then of course, there are many people that would like to see if they can then explain that, or if they can come up with a theory that would explain that, which could, of course, be a potential future Nobel Prize. So it's perfectly understandable and very useful, because then more people look at it. So, but yeah, eventually data is king, right? And after a while, we know, so we get more data, and then we see what sticks. Then it's a real thing, and if it goes away, then it was not.
Great. Yeah, so this links also nicely to the next question that we have. So how does ATLAS compare to other dark matter searching methods? So you already touched on this a little bit in your talk, but maybe you can go a little bit further. And then also, how much data do we need or want for these different kind of measurements?
Good questions. Yeah. So I think, yeah, we really use fundamentally different assumptions and strategies. So what's very different for us is that we don't rely on any assumption or rely on our knowledge about where the dark matter is in the universe, how it's distributed, and how it's moving. Because we produce our own, or we would like to produce our own in these collisions. And so there we have, we rely on very different assumptions. And if we, just like we said, if we were to see a signal, an excess of events that have this missing momentum, then this would certainly be very interesting, and people would think about what kinds of models could predict this. How would these models look for these other experiments? But I'm not sure how to answer that question, actually. What was the second part?
So the second part was how much data would we need, either for us or for these other types of experiments?
Yeah, I think that's very hard to answer. We don't know how much data we're going to need, right? We want all the data we can get. And right now we're planning to, well, it's already decided and we're underway to really upgrade our detector for running in 7 years from now. And we have these really long timelines, and we have to, because they're really complex projects and really complex to build these devices. So, and that's with the ultimate goal of getting 100 times more data or so compared to many of the results that we produced so far. Yeah, I don't know. Then of course, after that, since these projects take so long to plan, we really need to start thinking now about what the next facility would be. And this has been going on especially during last year with the European strategy update process, discussing what should be our priorities, what are the main scientific goals, how can we best measure the properties of the Higgs boson, how can we really scrutinize the Higgs sector, and can we measure its self-coupling, and then of course at the same time, how can we reach higher in mass? Can we produce collisions with much higher energies? So there is a plan taking shape for that, but this stretches over many decades and probably beyond both of our careers, I would say.
Yeah.
So it's exciting and fun to think about, but we also need to work on the things that we're doing now and plan for the future at the same time. But we want all the data we can get, I guess, is the summary.
Yeah, well, we're fortunate to be able to use the detectors that were built before our careers started, or the facilities that were built before our careers started. So it's also, I guess, our duty to build the next set for the next generation of scientists.
Yeah, exactly.
So to follow on from this topic, so one of the questions was which detectors are detecting these dark matter type events, or potentially detecting these dark matter type events?
So sorry, what kinds of detectors?
Yeah, which kind of detectors? I think you mentioned a few, but
yeah. So right. So I mentioned a couple, but there are also lots of other interesting ideas, especially for scenarios with axions, for example, that really require completely different instruments. And there are several of those that are in the works. And typically those are not as big collaborations as the LHC experiments are. And there are plenty of cool ideas for direct detection that also have much smaller communities. I don't want to start a list because I know it's going to be incomplete and it doesn't help most people anyway, I think. But there's really a lot of cool things going on, and lots of fun, inventive new strategies to try to target specific scenarios and specific corners of parameter space.
Yeah, and I think, as you mentioned earlier, it's good to come at this from all angles. So because we don't know what it is, we have to explore lots of different ways it could be either created or measured.
Absolutely, yeah.
Yeah. Okay, so next question is, could dark matter interact with itself, and what would that imply?
So this we don't really know. There are models that say that it would. Of course, if it doesn't interact at all with itself, then some of the strategies that we discussed already are out the door and wouldn't ever give a signal. So yeah, there are many different options here, but at the very least, I think we all expect that it would interact through gravity with itself. Otherwise, we probably wouldn't be in this universe that we have now. But there are very many different models and theories for dark matter, and with varying degrees of self-interaction.
So again, as a nice lead on, does supersymmetry explain the mystery of dark matter? Is this one of these models?
I still think it could. Yeah. So there are people who are super religious about what their favorite model is. I don't see myself as having those kinds of opinions, at least. I think it's a beautiful theory. It's a beautiful framework. And there are lots of fun signatures to go and look for. But they could also, those same signatures in our experiments could also come from other theories. And we should also try to be objective and not necessarily look only for specific theories. We can look for signatures and scenarios that are motivated by solid theories, but then we should also look for other things. I think we need to look for everything. You know, thinking about the discovery of the cosmic microwave background, we should also just like investigate everything in our detectors super carefully, and you might stumble over the biggest discovery ever.
Mm-hmm. Check whether the pigeons are roosting in them.
Yeah.
Well, so you've already answered one of our other questions, which is, or sort of not answered it, which is, what is your favorite dark matter theory? If you had to choose, which one would you hope it could be?
I can't really say that I have a favorite, to be honest. I would, okay, here's my, it's a bit of ducking out, but still, I would love to be just surprised and it doesn't match any of the predicted scenarios. That I think would be the most fun. And that we get to, yeah. The other part is, of course, the dark matter theory that we can find. I would love to be true.
Yeah, that's quite,
that's more of a characteristic, I guess, than yeah.
Yeah, I think that's nice. And I think that's also why many of us got into science, is that we want to find out about the universe and we want to be surprised and find out things that no one has ever known before. So being surprised is a good thing.
Yeah.
Okay, so we've got 2 more questions for you, and we're going to broaden it out a bit more. So one of the questions is, how busy is your schedule for doing ATLAS research, and what do you enjoy most about your work?
Oh, wow. Yeah, my schedule is busy. I work a lot. So basically most of the time is spent being in meetings and writing emails and discussing with people. I do love to write code, and I do love to make plots myself and really study the data. But it doesn't happen as often as I'd like to think it does these days. So yeah, maybe that starts a bit. But then I think it's also, so I spent today, just before this, I was teaching lab exercises. Actually, the students were analyzing Open Atlas data, and there were 2 groups back to back for a total of 6 hours, and that's super fun. Also, I think so. Yeah, that's not my Atlas work, but I weave in my Atlas work into my teaching. So there's some synergies there, I guess.
Very nice. And I think that's also really great to mention the Atlas open data. So if anybody wants to go and have a play and learn about what we're doing and how to analyze data yourself, then we have this whole set of open data on our website. So if you just search for ATLASexperiment open data, then you can be a researcher yourself and see what you can discover in that.
Yeah, and I think that's important, right? I mean, we do this research, and it's of course funded to the largest extent by tax money from all these different countries all over the world, and this science really belongs to everyone. And it's kind of incredible that we get to do this, and that we as society has sort of constructed this method where some people who really want to go and dig into this detail can do that. So that's cool, but then we should also share whatever we can of that. And of course, our data, once we've looked at it and we think we're pretty happy with it, then we should just let that out, let others enjoy it and poke around in this weird world.
Excellent. Okay, so we have one more question for you, and you've just discovered dark matter and they let you name it. What would you call it?
I think it's already named, isn't it? It's called dark matter, right?
But what happens if it's a particle or? and you get to name the particle. If it's not one of the supersymmetry.
I mean, usually they're named after the person who came up with the theory, right, of it. So I don't think it would be me. I don't develop a lot of theories. I don't know. I've never thought about that. That's a good question. I have no idea.
So, I mean, I can say I have a choice. I think we should call it after Vera Rubin. I think the Rubin particle would be a very nice addition to our model.
Yeah. Rubino, maybe.
Yeah, if it's, yeah. Great. So maybe if people watching, what would you name it? Maybe you can put it in the chat or in the comments and let us know what you would call dark matter if you got to be the one that named it. Okay, and we're going to wrap up there. So we didn't manage to get to everybody's questions, but we're going to let Christian go home for the evening because it's already been a long day. Thank you so much for joining us and for the talk. It was really interesting, and we had a lot of thank yous in the chat for the presentation. So is there anything you want to close on, or?
No, just thanks for the opportunity. It's rare that we get a chance to take a step back and think about what all of this is like for the sort of general public. Usually we sit and think about why a line of code doesn't work or banging our head against a problem. And it was a great opportunity to get a chance to zoom out and think about the big picture. It's actually, it helps quite a bit for motivation, I think. So it's good for all of us to do every now and then.
Wonderful. So thank you again, Dr. Christian Ohm. And thank you for joining us and watching along live, or thank you for watching this later if you're catching up on the YouTube channel. If you have any questions later, or if we didn't manage to get to your questions, then please put them in the comments and hopefully we can get someone to come and answer those for you later on. So thanks once again. Have a nice evening or day or morning, depending on where you are. And we'll see you in the next live. Bye.